Lambda max is the wavelength at which the electron emits the highest intensity when returning to the ground state of a previously excited atom. On an emission graph, it's set up as wavelength versus intensity. Intensity is the number of photons emitted at a certain wavelength relative to the total number of photons emitted. Wavelength represents the wavelength of the photon emitted, which determines the color of the photon emitted. The composition and atomic structure of a molecule controls the lambda max because both the red and green dye have a unique molecular structure. The molecular structures determine the quantum energy required to excite an electron, which is what determines the wavelengths at which the emission spectrum has peaks. At a given lambda max, multiple colors can exist because lambda max only represents the highest peak within an emission spectrum, not including all of the lower peaks that contribute to the color of the substance. This can be seen in our data when both the red glow stick solution and the mixed glow stick solution have the same lambda max. The mixed glow stick solution has a second peak at a lower wavelength, but it still has the same lambda max as the red glow stick at a lambda max of about 616 nanometers. What determines what color is emitted the most depends on the available energy levels of the molecule. Both the red and mixed dye were able to have the same lambda max because they both had the molecular structure of the individual red dye in them. Because of these differing molecular structures shown in the image given, their structure will determine the available energy levels of the electrons.
Electrons can be excited just as elevators are able to take people up to another floor. Elevators will go up and down to specific floors based on which button is pressed. Likewise, depending on the specific amount of energy added to an atom, the electron will jump a specific amount of energy levels. Additionally, just like an elevator, electrons will not stop between floors or energy levels as they require a specific quantity of energy to jump. This is why the peaks occur at specific wavelengths, because wavelengths are inversely proportional to energy. Electrons will not remain at the excited state and will return to the ground state, causing an emission of light. This is like when an elevator returns to the bottom floor to pick up more people. In other words, the ground floor of an elevator can be compared to that of an electron at its ground state. For the electron, it's more energetically favorable to be there as the state requires the least amount of energy. Likewise, for the elevator, it's more likely to be on the ground floor as that's where most of the people are. This elevator analogy doesn't completely hold, however. For instance, in electron excitation, if an electron is further away from the nucleus, it will require a lesser quantized energy to jump a level because there's less attractive pull on the electron from the nucleus. For instance, the electron would have to absorb less energy to jump from level 1 to level 2 than from level 3 to level 4. With the elevator, all floors are shown to be equal distance apart, thus not completely showing the different amounts of energy needed to jump between higher levels as discussed before.